Hello.
Yes, sir.
Hi. So, you guys are here? Good. Um, so tell me, what did you do in the last 4 days? Did you guys go over the this perceptual learning algorithms proof?
Yes, but proof like the algorithm given there is kind of different to the one we discussed.
Is it exactly the same?
No, I think they're different.
Why are they different?
Yeah, just a second.
Sorry. Yeah. So maybe if I can let me share my screen. Okay, you can see my screen. So this is the write up, right? This is the write up, and this is the proof. This is the algorithm. Correct. So they are going over all the possible training data. This Y1 to YT kind of stuff, right? And if it sees a T such that you have this YA is yeah. So basically, if Y, I mean basically whatever this means is that if YT is not equal to sine of xt dot theta, you update theta. Theta equals to theta plus yt dot xt.
This has a given number of iterations. Our
Uh,
algorithm,
right, it's the number of iterations t, right? Now, what is the number of iterations t? What is the number t? Has it told that?
yeah, they defined it using gamma square and R square.
Exactly. So it's the same thing, right? I mean, so the reason this will work is because whatever I told is that I told that don't stop, right? And here they say that okay, you have a fixed upper bound. And what you can see is that what exactly their proof says that if you just keep on doing it, right? So every time, so what is the proof actually? Right? That every time you do something, right? Every time you do some stuff, your this theta k dot product with the optimal theta star is increasing by a additive factor of gamma, right? And the other thing that is here is that theta k, whatever it is, at whatever point it is, right? It is upper bounded by this quantity, right? Which means that theta k plus 1 is less than k times r. Correct? So if you so you have this one. So that means what? That you have this theta k square. We know that this is at least k square times gamma square, and this is equals to kr square. So the k is here, so t is not coming in the picture. All it is saying is that if I repeat the iteration k times, after that we will get such an equation. Correct? So how many times, just don't think that t exists, but think that how many times that can the t happen. This t can happen at most r square by gamma square times, because as soon as the number of times the iteration happens becomes more than r square by gamma square, I cannot have this equation any further, right? Which means that if you did not have a bound on t, if you had not fixed a bound on t, it would have automatically stopped at that after r square by gamma square iterations. I mean, here what they have done is that they have told that, okay, I will put an upper bound of r square by gamma square. The basic idea is exactly the same. The other thing that you should realize is that if this algorithm actually gives you a right thing, then when can it actually give you a right thing? This algorithm, although they have given you a number of iterations, is capital T and all those things, you cannot expect to get a correct output unless you don't get any such a thing. Then for every t, yt is exactly equals to sine of xt dot theta. Right? So it is a bit convoluted way of proving it if you want to think of it that way. But the main idea is that this algorithm is giving you the right answer, and this kind of argument says that the number of times the iteration happens cannot be more than r square by gamma square. Is this clear?
But sir, r square by gamma square may be very large.
Good. So r square by gamma square is not something which is a fixed constant. That I completely agree. Okay, but this is how it is done in the standard literatures actually. See, first of all, r you can always assume to be equals to 1. Okay, I mean, if you think of it, initially we thought that these x's are of all of them are basically weight 1 or something. So r squared you can think of is 1. I mean, it is no big deal. Basically, you can think of all the x's are on the ball, on the unit ball, right? Now, gamma square, of course, gamma square can be very small. I mean, it is strictly bigger than 0, but it can be very arbitrarily close to 0 almost. But that's the thing, right? If it is arbitrarily close to 0, you expect that the total number of times, total time taken to find that exact bound, meaning you don't have any regal space, right? There is a hyperplane that is very tight. Correct. So in that case, you will take a lot of time. But usually, when this is applied, usually there is a decent amount of separation that comes. Okay. So, I mean, so yeah, it is true that this is not exactly, I mean, you cannot say that this for everything, it is upper bounded by some quantity and all. But this is upper bounded by a quantity that depends upon the input. Okay, and for most of the cases where it is applied, there is a decent separation. And this is how it is applied. The other thing that it is done is that usually it is applied without the upper bound of t. It keeps on going, and at some point of time, you realize that it is not outputting it is still not stopping. It can mean two things. Either these things are very close. Okay, I mean, these two classification, this pluses and minuses are very close to each other. So that is always a very complicated thing. If they are very close to each other, then should you really distinguish between them or not? Okay, so that is something like I told about handwriting recognition, right? I mean, can it be possible that the two digits are basically very close to each other? That is not expected, right? Or there is, of course, another possibility. This is something that you say that if it doesn't stop, it possibly means that there is no linear separator. I mean, we go ahead and the assumption that there is a very nice linear separator, and if there is a linear separator, you find it. But it is possible that there is no linear separator. Right? So any other, is this clear or? Okay, so I would start with a polling thing today about who all have read what, because I really need to know this thing. And so let me just start this. I have, of course, given you this 3 chapters to read as well as the perceptron learning algorithm. Okay, so more or less what I can see is that people have read the chapter 4.6, which was the union find data structure. And people have, half of you have read the chapter 3. And the other thing that I realize is that half of you are sleeping in the class because you have not even answered. So, okay, so what I would like to point out is that so among the people who have not read 4.7, okay, note that this 4.7 is a very interesting stuff. Why? Because this is also related to data, your big data analysis or something like that. So if I share my screen once again. Yeah, so basically what we have done so far was the linear classifier, right? Linear classifier. In which we assume that there are two different things. There are either pluses or there are minuses, right? And the assumption was that, if there exists a kind of a separator, a linear separator through them, of course that passes through the origin and all those kind of stuff, then you can try to find it. Now, of course, one thing you can always think about is that we have done it about a hyperplane. This as a separator, we have thought out hyperplane through the origin. And this was the perceptron learning algorithm. A natural generalization that you can think of is what about an affine hyperplane, right? Now, what is a affine hyperplane? Affine hyperplane is nothing but a shifted hyperplane that doesn't necessarily go through the origin. Okay, so just a shifted hyperplane that doesn't go through it. It's like a this one plus a constant. How do you do it? I would encourage you guys to think about it if you can. I'm not going to talk about it that much. Okay. But I mean, you will of course read about them at in the maybe in your some other courses if you have in your masters maybe or something on big data or something like that, or machine learning or something. The other thing that can say that see this linear hyperplane is always a bit vague. Now think of, I have a data of this form, okay? I have some points over here, some red points over here. I have some blue points over here. I have some green points over here. Maybe I have some yellow points over here. Oh, can you see? I don't know if you can see this yellow color. But whatever, something. So this one has multiple levels, right? So there are different levels. And now I will give you a point and say that, okay, this is a point. What is the color of this thing, you think? What do you think is the color of this point?
Red.
It, from a human eye, it is obvious, right? It should be red. Or if I give a point over here and like, oh, what is it? What is the point? It should be yellow. The main idea is that in our head, we are managing to partition this whole space into some kind of a clusters. Something like this, maybe. Okay? Something like this. Now, this is almost exactly same as what we do for many things in real life, actually. Okay. Now, like I told about this handwriting recognition, but handwriting recognition doesn't happen between 0 and 1, right? You have a handwriting recognition between of digits, which is 0 to 9. And usually what is kind of, if you look at the whole pixel, if you look at a picture of 0 or a picture of 1 or a picture of 2 and so on, and if you plot, I mean, it has a multiple pixels, if you plot them in a so if this has a n pixels, right, or n cross n set is the size of the pixel stuff. If you plot them in a n square dimensional space, where each point in the n square dimension says that what is the maybe the intensity and color of this particular pixel or something, right? So then you can actually, I mean, I don't have the graphics with me, but when people have plotted it, and I found out that these actually look like some chunk of things just hanging around here and there. Okay, and it's very clear that they form kind of what they call as clusters. So cluster is not necessarily a hyperplane or any such thing, but it is just the partitioning of the whole space into chunks. Okay. And the main idea is that you kind of, once you have, so the main issue is that, say something like I have a point over here, say, right? And sometimes maybe they are not of different colors. Okay, let's say that they are no different colors. So maybe I don't know how to make them. So let's say that none of them are of different colors, right? So it is so all of them are red. Say. Okay. And then I have to still kind of cluster them. Say something like, I will give you an example. Okay. So you have a friend who comes and says to you that, oh, see, I like this kind of movies. Okay. Or say if you say download or I don't know whether you guys watch movies in the internet or something like that, but or in the YouTube or something. Say you have a certain, YouTube gives you these various recommendations kind of stuff, right? Once you watch a video, there are lots of other videos that comes up on the site. How it works? It works is that it seems that the people, like, let's look at the set of videos that I watch. Okay, that kind of is in a cluster like this maybe. The set of videos that you watch, that forms a cluster. So the idea is that if somebody now, so although YouTube doesn't know that there is a cluster over here and there is a cluster over here, it kind of associates that, see, these points are close to each other. It means that these points possibly have something in common. And so if somebody else comes up and watches a video over here, it can say that, oh, see, you are here, so that means you must be liking the points on this cluster. So, however, I would watch this one, and something like that, right? So, in other words, what I'm saying is, sorry, this is not useful. So, if I say that, say, I have some set of points, and they are no colored red or blue or any such things, right? But there is a set of points in the hyperspace, and they can be all over the place. And just by looking at this collection, you kind of automatically possibly associated in your head that there are 5 clusters, right? Although I have not even told which is what cluster. So basically, you kind of in your head have decided, they have kind of thought that maybe something like this is a possibility cluster, right? Or in other words, this set of points, this set of points, this set of points, this set of points, and this set of points are clusters, right? So this is kind of the most important, the very interesting things to do. So basically the problem that comes out is that I have a set of points x1 to xn in R to the power some dimension d, and I want to say cluster them into say k clusters. Now whatever the clusters k means, okay. Now in that case, what is the best cluster that you can think of? Right, so say maybe if I remove this boundaries that I have told, so in this example, say something like this. If I told you that, okay, can you cluster them into 5 clusters, then you could have made them into this 5 cluster that was there. But if I told you that, oh, can you make them into 3 clusters, then what would you have done? Most likely you would have told her, okay, fine, in that case, mostly this is a cluster, this is a cluster, maybe these two are together a cluster, and this is a cluster, because this seems to be, they are more or less close by. If I've told that, okay, I have to cluster into 3 clusters, then most likely you would have told that, okay, I think this, all 3 of them are kind of looking similar, the other 2 are far off, right? So the goal is basically to cluster these points into small clusters. So this is a big problem in machine learning. How do you cluster them? Now, of course, there are lots of optimization that has to be done here, right? Like, I mean, as somebody, one could have told that when I picked up for 4 clusters, why did not you cluster, say, these 2 together and this one is separated? This is also a cluster. Who told this is not a cluster? Maybe I could have done that, right? So you want to cluster them to maximize something. Okay. Now there are a lot of maximizations that could have done. For example, I would say that the average point over here in each cluster, there is an average representative. The average of all these points or the CG of these clusters should be furthest away from each other. That is one way of saying it. How is the CG calculated? You can say that it is a median or it is the mean of the points in the cluster. This is one possibility. Or you can say something like, I want to cluster such that, say, so among the all possible clusters that you could have done using this, say, K clusters, right? Look at the distance between the closest points. So these two are closest, say these two are closest, say these two are closest, say these two are closest. Among all the closest points, right? So there will be something like K squared different possible combinations, or K choose two different possible combinations, right? And in K choose two different possible combinations of these clusters, you look at the smallest distance between points in those two clusters. Okay, so something that, okay, see this cluster, I have this cluster in which there is one group and another group, and these groups are separated by at least the distance d. And I want to, so the quality of the cluster is the minimum distance among all these points. So if the clusters are, if I have a cluster C1, which is basically, I mean, I will use the word cluster in two different ways, say C1 to CK, and I have another cluster C2, which is say, so maybe I have a cluster C that is this one, and I have a cluster say C bar, which is C1 bar to CK bar, right? So the quality of the cluster, okay, or maybe the I will say value of the cluster is what? Of cluster C, say. So this is the minimum, right, over all ij, the distance between points in I and points in J. So in Ci and Cj. Right? So for any cluster, I can define the minimum distance. So this is the kind of the value of the cluster. And note that the lower the value is, the worse it is, right? Because if the value is low, that means in this cluster there are, so if I have two clusters, right? So I have a value of the cluster C bar, and if say the value of the cluster C is less than value of the cluster C bar, what does it mean? It means that in C there are these two groups that are very close to each other. Whereas in C bar, all the groups are a bit further away, right? So you want to find, so goal is to find a cluster, find the cluster that maximizes the value of the cluster. Right. So among all the clusters, so there may be C, there may be C bar, there can be a lot of other clusters that are possible. You want to find the cluster that kind of have the maximum separation between the groups. That would kind of be a very natural choice to have for clusters. And what is proved in 4.7 of the Kleinberg-Turtles book is exactly how can you find these clusters? What is the way of finding clusters over there? Okay, and how that can be done using basically the algorithm of the Kruskal's. So, so for people who have read it,
Sir,
yeah.
can you once again say what is E and what is E bar?
So yeah, it is two different clusters. Okay,
And
so
we are
maybe
comparing between them.
and we are comparing between them.
Okay.
Which cluster is better? Right? There is of course a lot of clusters, right? There is not an infinite number of clusters. How many clusters can be there? Technically, there can be k to the power n clusters, right? Because each element can go to one of the k clusters. So there is k to the power n clusters. So among these k to the power n clusters, I want to find the cluster that maximizes the value. Right? So cluster is nothing but a partition. What is a cluster? Cluster is nothing but a partition of the points into groups. And I want the value of a cluster is the smallest distance between 2 points of different groups. One coming from one group and the other coming from the other group. Okay. I mean, my goal is not to necessarily give you the most formal definition here. My goal is more to give you the intuition about why it is interesting. Oh, hello, am I there?
Yes, sir.
Yes, sir.
Okay. Well, my internet was a bit tricky suddenly. So anyway, so of course you can get to know of the exact rigorous result and rigorous concept of clusters and so on in the chapter 4.7. And it's a very interesting one. I mean, I assume that for all of you, learning about machine learning is one of the interesting stuff, and no doubt this is one of the very interesting areas of research and applications that is there. So, so clustering. So, in fact, what we have seen in these 2 days is one thing we have is what is called a classification. Classification is when you separate into 2 parts, usually by a line. Okay, and clustered a line or a curve or something like that, or a general manifold or something. And clustering is basically when you cluster the things into clusters. So in the first thing, what is told is that you have been given labeled data. Meaning there are data which has some of them have been labeled plus and some of them have been labeled minus, right? In the clustering, you don't have any labels. So they are a set of points and you are supposed to look at them differently. Okay. And so something like, say, think of it yourself, right? If you suddenly see a weird looking creature like a, which is closely related to a cockroach kind of stuff, you will immediately say that, oh, that is kind of like a cockroach, it is an insect, that's me. So that means in your head, you have an idea about what an insect is. So the insects form a group, right? Although nobody has told you that that is an insect or something like that. Right? You kind of had the separation already. So this is unlabeled data. Or sometimes this top one is called a supervised learning and this is called a unsupervised learning. So 2 of the most interesting concepts of machine learning. Of course, we are just scratching the surface. In the classification, we only looked at linear separators going through the origin. it can be much more complicated, no doubt about that. It doesn't have to go through the origin. It can be a manifold. It can be very weird objects and all. Okay. And clustering also, we just have looked at it in this thing. And then the question comes out that what happens, so these points are all in a very high dimensional space. Now, if you really want to access a very high dimensional space, then that's a lot of cost incurred. How do you reduce the dimension of the points, right? We are kind of almost assuming that, oh, whenever all I have to go is that I will look at this point and this point and say, oh, what is the distance between these two? But finding the distance between 2 points in a 1 million dimensional space is not at all easy, right? So that dimension reduction and all those things will come up and all. Sorry, there is some noise in the background. Okay, so is that, does it make sense, whatever I told? Are you guys motivated enough to read 4.7 now?
Sir, are we categorizing this classification and clustering on the basis of learned data? Because in real life, the data, there are no such labels with the data.
In real life, there are a lot of labels with the data. Okay, I will tell you one kind of labels of the data that happens a lot is that, so you know, nowadays there are these voice recognition kind of softwares, right? Do you know how it was done? It was actually done by making, so I have to just say the simple things. To start with a very simple thing. I want to have a software that if you say yes or no, I will understand whether you are saying yes or no. That's it. Now I have to be able to understand yes or no based on, I mean, irrespective of what the accent of the person is, whether that person's voice pitch is high or low, whether that person is a male or female, whether the person has an American accent or a African accent, everything, right? So the way intelligence is done is that they pay people, a lot of people, to come and say the word no, and for them to say the word yes, and that is put into the machine. So that is the labeled data. Okay, so there's a very nice label that has happened. And now you guys, then you kind of doing so. After doing so, after enough amount of training of the program becomes smart enough that it can identify it. In fact, I don't know, I mean, you guys are too young, but when I was in my PhD times, that was the time when this learning of the voice recognition softwares and all were coming up. And you could, I mean, so the initially set of things that came up was really irritating. Like they say, in the phone say, so do you mean yes or no? And then you say, oh, I mean yes. Then you say, oh, so you mean no? Or no, I mean yes. Then after all of these things, they say, okay, fine. If you are saying yes, then press 0. If you are saying no, press 1. So the idea is that they will use that thing to kind of use my voice to train itself. And within a few years, I saw that the voice recognition softwares have improved drastically. This is a very natural thing that happens. Another thing that is going on a lot nowadays that I know of is something like identifying, say, in Twitter or something like in LinkedIn, they want to ensure that nobody uses slang words or they don't use an obscene language. How do you catch that? And one of the ways is somebody has to come up and say that, see, this is a slang word and this is not a slang word. And that's the labeling that happens. And once you have enough labeling kind of stuff, then the algorithm hopefully will be able to catch it. Some other combinations of something and all. The clustering kind of stuff happens. For example, things like clustering is a lot more tricky, because when there is no obvious way to understand the separations that happens, right? I mean, as I told, I mean, your choice of movies might be based on some very weird set of dimensions. So your choice of movie has a clustering in itself, and you possibly don't even know yourself. How can you explain what kind of movies you like? But if I know the kind of movies you like, or kind of movie that you liked, then I would be able to understand that. Okay. So such kind of stuff, such kind of problems that comes up. So if you guys are interested in this kind of stuff, I would suggest that there are a lot of online programming, online competitions and all those things for data sciences. One of them is called a Kaggle. I mean, so there are a lot of problems which are very algorithmically interesting, have a lot of this kind of a data science flavor to it. And the goal is to kind of do something like that. Yeah, so there's quite a lot of such things. Yeah, I mean, another story that I can talk about as the clustering technique is that. So, have you ever heard of something called a Netflix problem? Netflix challenge. So Netflix challenge was something that, so you know Netflix, right? It is one of the online movies watching portals and all. And so Netflix was there for a long time, even before the online thing started. It used to, I mean, you could borrow DVDs and all from Netflix and watch it. And Netflix told that it kind of released a collection of a part of its data that it had. And the idea was that all you can see there is that, okay, this person has watched these movies. Okay, this other person has watched these movies, and so on and so forth. Okay, what are the movies you don't know? The movies are I mean, they have been given an artificial name, and there's nothing else is known about that. Similarly, I mean, all of this kind of stuff are there. And now the idea is that if a new person comes and watches a few movies, you have to say or pray, you have to kind of give a recommendation to that person that, oh, see, why don't you watch this movie? You'll like it. And if that person likes that movie, then you have succeeded in your prediction algorithm. So Netflix gave an open challenge to everybody saying that, can you please, I mean, whoever can beat or give a very good prediction algorithm will win a lot of money. And it was a big challenge for a long time. And I think it still might be on, I don't know. But it was basically coming up with a very interesting clustering algorithm. Of course, it has a lot more interesting stuff than whatever I'm saying now, or whatever we have done so far. But basic idea was same. Okay, there are a lot of stories that tell you that are happening. So, yeah. So among the people who have read chapter 4.7 and the perceptron learning algorithms, I mean, if you have any doubts, let me know. And the rest of you also, if you have any doubts, let me know. But I hope that you are motivated enough to go and read those stuffs. Hello? Any questions?
Yes, sir, we can hear.
Sorry, somebody saw something I could not hear. Hello?
Yes, sir.
Huh?
Yes, you are audible.
I cannot hear you somehow.
Hello.
Is it my voice or my probably my end or your end? Hello? Can other
Yes,
people?
sir.
Yeah. Tell me.
Sir, in the perceptron algorithm,
Yeah.
I could not understand that wait, something it was gamma square in the
Yeah.
denominator,
Right.
and you said that it depends on the input,
Yes.
but if it is depending on the input,
Yes.
and it may be the bound may be very large, so how can we calculate the time? Or,
You don't have to calculate the time, right? Why do you have to calculate the time? So, okay, you can simply say that, okay, first of all, you can do that. You can compute the gamma, or you can, maybe gamma is there, but you don't need to, right? The idea is say that you keep on going, let it go, and it will stop after this much amount of time, for certain, after this much amount of steps. And you don't have to give it a upper bound or after how many times it should stop. The algorithm, you can have an infinite loop. Say that, okay, unless you have found this stuff, you should not stop. Right? And what this says is that after r square by gamma square, whatever the number is, it would stop. Right?
yes, sir.
So yeah, so since you know r square, right? R square calculation is very easy, and you don't know say gamma square. Right. The main idea is that, so first of all, it says that this algorithm has a finite stopping time. You have a bound on that, which is r square by gamma square. And of course, if the gamma is very low, it can take some time, no doubt. But I mean, in practice, what is done is that it is usually run. People let it run for some time, for a certain amount of time. And if the algorithm doesn't stop by then either you kind of decipher that, oh, see, then these two objects, the gamma is very small, or you decide, or you kind of say that all these things is not a linear classifier. See, this is also another thing, that if the gamma is very small, then actually it is not 100% sure that whether it is whether uh, uh, linear classification is the right thing to do. Because gamma is very small. I mean, in real life, you don't get examples where you have like classes. I mean, like it's like there's a very tight separation between pluses and minuses. If that is the case, then you realize that, oh, something is not right. It can happen, of course, it's an artificially created function setting, but such a setting doesn't happen. So then this is possibly not the right linear classification is absolutely not the right thing. Okay.
So sometimes it may happen that the efficiency of the computer is not so high, so it cannot recognize the line or classification, but actually there exists a such line.
There exists a such line. Again, see, it is all about the number of steps that after which it goes is r square by gamma square, right? You have no issue about that. And now, whatever, I mean, depending on the computer, if you run your algorithm on a big computer, people will know that, oh, that means this many number of computations means it will take some 1 day or something like that. So you are saying that it is all about this. I mean, theoretically, whatever has been told, that it stops after r square by gamma square number of steps. The algorithm, you can let it go and it will stop after this number of steps. Okay, so it is not, the crucial important part here is that the beauty of it is that it is not an unbounded thing, and you can get a upper bound on after how many steps it will stop. Now, if the gamma is actually very low, then that goes into the realm of the practitioners. Okay, so usually when people doing the practicing stuff, they use. I mean, when people are running on some big computer or something like that, or a computer, you know that after this much time you will not happen or something. If it doesn't happen, then I will make a call on that. See, here I should be a bit careful here, because although, as I told you, that this course and my own research is very much theoretical. Okay, so we only talk about the theoretical aspects of it. But it is also important to note that any of these algorithms are also used in practice. Okay, and when you use it in practice, then there is then there's sometimes a bit difference there. Okay, that has a lot of other structures that you have to kind of know about, how to program correctly, how to make some calls, and so on. See, theoretically, I can say whatever is going on here, but in practice, when people apply these algorithms for finding a hyperplane or something, it is not that they are trying to really test out whether the algorithms are working for the worst cases. They just want to find a hyperplane in a natural setting, right? And that natural setting, usually the gammas are not too small. Or if the gammas are too small, then that is not a very good setting. Then a linear separator is not something that is the right way to look at it. So that is how they think of it. So there is a slight difference between, so we talk about the worst case and all of those things, but the real life, this is exactly what happened in the case of perceptron algorithm. When the biologists were applying perceptron learning algorithm to their problems, it was stopping at a super fast pace. It was coming up with a linear separator very quickly, but they had no idea why. Now we gave an upper bound, and of course you say, oh, then that means their data were most probably far enough. So yeah, that is the case, that their data were far enough, and that's why it was stopping. If there was their problem where the gammas were very close, very small, then it would have taken a lot of time. But that doesn't happen in real life. So possibly I will come back to this kind of difference between theoretical and practical algorithms a bit more later in the course also. But again, I should remind you guys, in this course, we only focus on the theoretical aspects, and whatever I'm talking about as the applications parts are mostly to motivate you guys towards this stuff and tell you how the things are there. Okay, it is exactly like the difference between theoretical statistics and applied statistics. Like people who actually end up going and applying some statistics to do certain stuff and all, they are, you know that there is certain difference between those two things, right? It is exactly this, the case here. Yeah. Any more questions, doubts, confusions? So by the way, I always think of my courses to be a way to kind of tell you guys, give you pointers to things to read and all. Okay. So although there are certain things that I'm supposed to teach you guys, but I also will keep on saying things which are like slightly out of the course and all. So this was one of these in which, it of course shows the power of greedy algorithm and how to compute it and all those kind of stuff. But it also introduces you to this concept of what is machine learning, what are the standard machine learning techniques. And if you guys are interested, you guys can, of course, Google for yourself, find out for yourselves, and keep on learning. Now, you guys are all smart people. You guys have very good background in mathematics. So understanding, things in of the clustering techniques or any of the machine learning stuff or data science is pretty cool, easy for you guys. So, these are like if you want, you guys can read the classifications and clustering stuff. Of course, there are lots of the theoretical aspects of that also, and then there are a lot of the applied versions of that also. either of them you can go ahead, or both of them. I mean, that's completely up to you guys, which way you want to do it. Okay, any more questions? No questions so far? Okay. Now, in this section 4. What was the last section that was there? 4.8, right? If I'm not wrong. Do you remember what was this last section that was there? I've forgotten. What was it that was there? What was it? Whatever. So the one next to the 4.7, 4.07, after this clustering algorithm, is what is called this Hofmann codes algorithm. I don't know. I mean, have you done this thing in your course, in a previous course in discrete math or something? Quarter Hofmann codes and something. Hello.
No, sir.
No. Okay. So.
So,
Sorry.
Hamming codes we did.
Oh, okay. What about you? Have done Hamming codes, right?
Very minor introduction that
That
was
to a very basic introduction to Hamming codes, Hamming distances, not much at all.
Hamming distance or Hamming code?
Hamming
We did
code.
actually a basic on coding theory in our linear algebra class.
Okay,
Over
very
there, it was taught.
Okay. Good. So you have seen a little bit of this coding theory. That is good enough for us, actually. Okay. So basically the idea is that, say, if you have to, so you have the English language, right? You have the English language, say A to Z, A, B, C till Z, and I will write some sentence or something like that, some literature in English, right? I have written some lines in English, and I want to send you that literature. Right? That's the standard thing that we do all the time. Correct. Now, how will you send it? Now, the issue is that we can send only strings of zeros and ones. Right? You can only send strings of zeros and ones. So you have to encode this one into a string of zeros and ones in such a way that when you get that, if this one is sent to you, you will be able to understand or decipher the actual language. Right? So how can you do it? Now the problem is that, say, what happens if I say, I can say, okay, so that means I have encode each of these letters into zeros and one string. So I can say that, okay, fine, I will write A, I will send a 1 bit. I will send a 1. For B, I will set 0. For C, I will set 1, 1. D, I will set 1, 0. And so on and so forth. Do you think this is a good code to send?
Sir, maybe we can say A is a string of, in every letter we can think of a string of 0 and 1 of length 5. Then we can assign every letter because 2 to the power
Okay,
5
fine, good. So good, very nice. Okay, so let's do that thing. So you are saying that you will just consider every letter A to Z will be assigned a length 5, right?
Yes.
And you claim that this can be done because 2 to the power 5 is more than 26 and so on. And you know it will be blocks of size 5. But do you think this is the right thing to do? Is this optimal? Of course, I can understand there that if you send this stuff, you will be able to, or whoever the receiver will be able to decipher the actual language, right? So you are right. It will be able to decipher. So I had two goals. Okay, first goal is that I have to be able to decipher, and second thing is I should try to make the string as short, right? Because sending this string should be as short as possible. Sending a long string takes a lot of time, lot of energy, lot of effort, lot of cost and so on. So this is a good thing for doing a good encryption, for deciphering correctly. But do you think this is the correct thing to send? Or let's say that if I have an English letter, okay, with n strings, what is the expected length of the encoding? Think of n to be going to infinity, the big number. So what is the expected? So maybe I would say the expected length of the encoding divided by n. What is that number? Here, of course, the expected length of the encoding divided by n is nothing but 5. So to send n letters, you are sending 5n length string everywhere. But can you do better? Can you do better? The main issue is that think that there are these vowels, okay, or let's say a. The a probability that a occurs in a string, a probability that a occurs in the English language, say is say 10%. Okay, so basically 1 by 10, right? So meaning that for every almost every 10th letter in the English language is a A. And probability that Z occurs in a string is 1 by 100. Do you think now spending 5 letters for A and 5 letters for Z, is it the right thing to do?
Sir, in that case, we can do something like we know the probabilities, right?
Yes, we know the probability is there.
Then we know what is the probability of what is the maximum probability. I mean, say A occurs maximum time. That 1 by 10 is the maximum between the 26.
Right.
So we can assign 1 for A and the minimum probability say for Z or Y, something like that. Then we can assign 5 string for them.
Okay, good. So you're saying that, so that means this letter that occurs lot of times, it is better to give it a shorter string. And for Z or something where it comes hardly, I give a lot of string. And the main idea is that if I have the probability of them occurring is P1 to Pz, then and I encode them with length L1. So this is the encoding. Encoding is done with length L1 to Lz. Then the expected length of a string by n, right? This would be what? It would nothing but summation of, forget summation, this will be equal to PA LA plus PBLB plus up to PZLZ. right? And your goal is to basically therefore reduce this L1 to LZ or determine the L1 to LZ in such a way that this is minimized.
Sir,
Yeah.
I have one question.
Right.
Like when we are encoding in this particular code, like if we want to write some word, like by default, is there a space between two or
Yeah, you can think of the space. So there will be a
written in
space.
such a way that we have to distinguish between the
Yeah. See, I mean, there is a space. So you can think of the space to be the 27th letter. Right? Hello? Is it clear? I mean, I cannot hear you properly. I don't know. I mean, they're not only space, and this is just for.
between we do not have to distinguish between and the letters like that.
In the encoding, right? In the encoding, you mean? Hello? Do you mean in the encoding? Spaces in the encoding?
Yes, sir. So like when we are writing any word, we do not have to distinguish like when one letter ends or the next letter start. That we do not have to care about right now.
If it was just 5-letter stuff, then we did not have to care about, right?
Yes.
But if it's not a 5-letter word, something like this, okay, which has been optimized to do something else, then we are a bit more in a bit tricky situation, as you guys possibly have already guessed. Say I have A, B to Z, and so see A is something occurs very lot of times. So I will give A, I will encode A with 1. Okay, I have also E, and that occurs a lot of times. So I encode E with 0. Maybe the next one that occurs is something like say U. So U I will encode with say I have already used 1 and 0. So I have to have 1 1. And then maybe there is a O which comes, and then I will use it to be 1 0, and so on. Now there's a problem here, right? Maybe by doing so, the lengths are so chosen that this quantity, the expected length of the string, or expected, this is called the expected blow-up, okay, or the rate of the code. It's also called the rate of the code. Rate because it's the average amount of bits you need to encode one word, one letter is what is. So, so while this was optimally done, there's a problem here. Why? Because if I, as a receiver, get something like a 1100, I really have no idea what are they. This can be AAEE. It can also be AOE. It can also be something else, right? So cannot decipher uniquely. So I have these two diagonally opposite problems. First, I have the problem of I can encode it very nicely, but then the rate is high. If I want to optimize the rate, then I am unable to decipher. So I need to put some more structure here. Okay. So the main clue to this one is that what you do is what is called a prefix free code. So what was the problem over here? Let's say the problem over here was that when you were reading, so this was a coding, right? This was a coding for 0, for O. Hello? Yeah. So this was a coding for O. But the problem is that there's a prefix, which is 1, right? Which is also a code word. So we call these ones as code words. So these are called the code words. Code words are for every letter, there is a code word. And this is not prefix free because here is the code word and here is the code word, and this code word the prefix of that. So prefix free code word meaning for every A to Z, I am encoding with something like what I encode. So let's call this one E of A is my encoding of A. E of Z is the encoding of Z. And I want to say that these are any two of them for all I and J between between A to Z. Okay, E of I is not a prefix of E of J. Right? Something like I can say that okay, I will have A to be equal to 0, 0, B to be equals to 0, 1, 0, C to be equals to 0, 1, 1, maybe D to be equals to or say 1, 1, okay, E to be equals to 1, 0, and so on. So let's just for sake, look at here. I have of course not done a very good job of saving things, maybe saving space, but if I say this, any collection of these stuffs over here, I will be able to decipher. Why? Because none of them is the prefix of the other. Right? So I start from the left. So if I give you something like say 0, 0, 0, 1, 0, 0, 1, 1, actually you will not be able to understand. Maybe is I mean, there are a lot of things that could have happened here and so on and so forth, right? But when you start from the left, you said, okay, 0, 0, there's only one thing that could have ended at 0, 0 also. This means this is A. 0, 1, is there anything 0, 1? No. 0, 1, 0, good. So this is that means this must be B. 0, 1, 1, oh, this must be C. See, that means a prefix-free code is ideal for decoding. So the now, okay, I have of course not proved that prefix-free code is ideal for decoding. Not ideal meaning it is decodable, it is uniquely decipherable. You go and prove it for yourself, or you read that chapter. But so what I need is that goal is what? To find a prefix-free code such that the rate is minimized. Okay, and of course we want to compare that whatever that rate is the best rate that could have been done if we don't have the prefix-free codes criteria. And how do you find it? How do you find one? And this is what is called the Hofmann encoding. Hofmann encoding. It is actually very simple, okay? So, but it's very beautiful. And this is what has been done in the other, in the last section. Okay, so again, I will really request you guys to read that sections and come back next class, which is on Tuesday. So all these three things, the union find, if you have read it and understood it, fine. I don't want to go too much into it. But 4.7 and 4.8 or whatever, there's two things. There's one of clustering and one of Hofmann encoding. The two things that I really want you guys to read it. Okay. And from the next class, what I will be starting to do is, I can find my, good. Yeah. So in the next class, I would be starting with Yeah, I will start with this 5.5. Okay, and I will start with 5.5 and 5.6. So I really request you guys, if you can, to read them before you come and at least get motivated by it or something like that. And yeah, but I'm not 100% sure if you guys are that, if you guys do it or not, but this is very interesting. And particularly for you guys, it will be very nice. Because here we will see some very non-trivial algorithms, how to multiply two numbers, two integers, and how to, this is something as a very useful thing for you guys, multiply two matrices. Okay, what is the worst case running time, what is the what is the trivial after running time, and what is the best that you can do, and so on. Okay, like this thing is also important because this is important for you to understand what is the running time for inverting a matrix, something that you guys need in many of your statistics problems. Like this whole, you need to invert a matrix and do something with that to do some predictions and so on. Basically, what I am saying is that please go and read chapter 4. Okay, if you have any doubts, let me know. Okay, and or come with the problems and doubts in the class. And in the next class, I will be starting with section 5.5 and 5.6. Okay, any questions? Hello? Okay, so then let's stop today. We will meet on Tuesday.
Thank you, sir.
Thank you.